Hello, everyone. Thank you for joining us on this Thursday, June 23rd, for this iteration of our Terra Insights webinar series. This time, we are happy to be partnering with Thurber Engineering to discuss integration of InSAR and space-based imagery in geohazard management and monitoring for energy pipelines. I'm Kyle Shatzer. I'll be your host and moderator here. I live in Minneapolis, Minnesota, and I'm a geotechnical engineer. We're also joined by Damian McClarty of Thurber Engineering. Damian is a geological engineer with extensive experience in geohazard assessment and management for pipelines and infrastructure. And Kris Covey of 3V Geomatics, part of the Terra Insights group, leads our oil and gas efforts for the last 5 years at Terra Insights. He has 15 years of experience developing new markets for emerging technologies in the energy sector. So those two will handle the bulk of the presentation, and I'll be kind of moderating some Q&A, and I'll wrap it up with just a little bit on some sensors, some of the physical stuff. So a little bit of logistics. Please use the webinar platform to ask questions. We will try to sneak those in if it makes sense during the presentation, but we'll also allow some time at the end for Q&A. We'll also send you an email follow-up with some of the resources that we discussed following the presentation. And with that, we are live talking to you today. So the agenda for this webinar, Damian will start it off with some discussion on geohazard management, involving not just InSAR, but LiDAR and some of the other tools that he and the Thurber team use. And then Kris will delve into some of the details of InSAR for pipelines, as well as data collection and delivery. I'll do 5 minutes on sensors and data collection, and we'll do Q&A. Real quick, Terra Insights, you may have seen this name, you may not have, but Terra Insights is the brand that's comprised of these 4 companies here. So RST Instruments, founded in 1977, does more of the traditional vibrating wire, strain gauges, MEMS sensors, and data loggers. Measurand, on the eastern side of Canada, focuses specifically on shape arrays. 3V Geomatics, one of the featured presenters here with Thurber, is our InSAR provider based in Vancouver. And Syscom is our vibration monitoring arm based in Switzerland. So these companies started joining together in 2019. 3VG and Syscom were added in 2021, and the Terra Insights platform was fully rolled out this year. We have over 100 degreed engineers. We're all over the globe, as you can see here, thousands of clients, and we've been focusing on instrumentation and monitoring since the 70s. So pretty exciting stuff, and we're proud to be the one-stop shop for instrumentation and monitoring. So with that, I will hand it to Damian to introduce Thurber, and he will talk about their background and get into the presentation.
Awesome. Thanks, Kyle. So Thurber is an employee-owned consulting firm established in 1957. We currently consist of approximately 500 or so geotechnical, geoscience, and environmental professionals throughout Canada. This is just a quick screenshot of our various office locations. And then we can dive into the actual content here. So to get started, I'll be discussing some key points for geohazard management programs for onshore pipelines, and then we'll pass things off to Kris from 3VG to discuss InSAR applications. This is going to be a very high-level overview of geohazard management practices, so please feel free to reach out after the presentation if you have any questions or would like to discuss any topics in more detail. While geohazards are not the most common threats posed to pipelines, the consequences of unmitigated or unmanaged geohazard activity are very high, and geohazard threats are often some of the most expensive to mitigate. On the slide shown, we've included some basic failure statistics taken from Porter et al. 2016 for pipelines exposed to geohazards in various regions around the world, just to provide some context as to the prevalence of geohazard threats to pipelines. Landslide-related ruptures account for approximately 8% of all pipeline failures, according to a 2019 AER bulletin, but are also typically much more expensive to clean up. So here we have a risk management model from Marlborough in 2015. And this is just to kind of give an indication of where geohazards fit within the broader risk framework and other common threats to pipelines. So the caveat to this model is that Marlborough's placed geohazards under time-independent mechanisms, but we just want to highlight that they can be either time-dependent or time-independent, depending on the type of geohazard that you're dealing with. So this is kind of our simplified breakdown of how a hazard management program typically functions in these kind of three main steps. So the first step is to identify hazards and develop an inventory of credible threats to the pipeline. This will typically involve developing some form of database to track hazards mapped in a GIS workspace, which we'll discuss in a bit more detail. And then the second step is to assess each identified hazard and the associated threat posed to the pipeline, which will involve some implementation of a ranking system, which can be either qualitative or quantitative, depending on the project context. And then the last will be to determine how best to manage each identified hazard or threat to the pipeline, typically focusing on those which pose a greater threat. So this can involve either acceptance of the threat, avoidance, monitoring, or mitigation, which again, we'll cover in a bit more detail later on. So the first step of the process is typically to identify and inventory hazards within your assessment corridor. So this stage can be scalable depending on the scope of the project and available data or ability to acquire data. Typically, this would involve some form of hazard mapping and screening based on credible or non-credible threats to the pipeline or whatever asset in question that you're assessing if you're dealing with other types of linear infrastructure. So if sufficient data is available at this stage, it may be more efficient to complete a screening level ranking system in conjunction with the initial mapping effort. On screen, we've got an example classification system from Doer in 2019, just to give some context. And then, so our preferred approach to hazard screening would typically be to acquire available off-the-shelf or pre-collected LiDAR data from vendors for the full asset corridor at about a 1 meter by 1 meter resolution. The data is less important for screening, and higher resolution data can be used, but we start to get a bit more noise from vegetation and other sources of higher resolution. So typically about that 0.5 meter to 1 meter resolution seems to be the sweet spot for geohazard screening. Screening can also be completed without LiDAR, but we've typically found that the additional effort required from the geohazard practitioners to interpret the publicly available data often offsets the cost of the LiDAR purchase up front. Although we would also review some of that publicly available information if we had the LiDAR available. It's just that it makes that assessment process that much more efficient. So once we have all that data in hand, we would map all assessments in the, map all hazards in the assessment corridor and complete a preliminary ranking in a hazard database. And then we'll usually record some kind of common observations for each hazard. So moving on to the hazard assessment piece. So this is typically a more detailed assessment of threats once we've had an opportunity to acquire some additional data or take a more detailed look at each. So LiDAR is kind of our main tool for assessing surficial morphology, landslide mechanisms, and we can also determine the relative age of the morphology that we're looking at. However, for most cases, for landslides in the Western Canadian Sedimentary Basin, it does provide some limited options for monitoring of ongoing activity. So basically, while we can determine from the morphology how recent or likely active a landslide might be, quantifying the movement through change detection from differential LiDAR data sets can be problematic just due to limited detection resolution. And, in the Western Canadian Sedimentary Basin, we're often dealing with these deep-seated clay landslides, which may have varying levels of surface expression. So they could be moving much more actively at depth than what we can detect on surface. And that limitation does apply to InSAR as well. So something to be aware of. But as I said, still an extremely useful tool for assessing landslide morphology and interpreting movement mechanisms. And that change detection can be a valuable supplemental source of information if multiple data sets are available. So while not as detailed as LiDAR, and typically the benefit is limited in areas with dense tree cover, historic air photos are still useful in establishing timelines for, say, anthropogenic activities or large-scale ground movements or changes in channel morphologies if we're looking at hydrotechnical hazards. Air photos are typically available for various years and scales, anywhere from the 1950s to present, and in some areas locally as old as 1924. So understanding these land use changes over time can be extremely important for interpreting geohazard activity and predicting future threats. And the historic air photo reviews really provide those valuable inputs that we can't get from other data sources. The next step would be actually going out to the fields. So these aerial inspections are often undertaken to confirm large-scale ground deformations along the right-of-way. They're useful in that you can cover multiple large areas in a short amount of time and get a current sense of conditions along the entire corridor. However, they're not great at detecting smaller instabilities or more subtle signs of ongoing ground deformation. And for this reason, if we're doing an aerial inspection, we would often recommend completing them with a helicopter instead of, say, a fixed-wing aircraft, so that you have the option to circle back or land and take a look at a site on the ground if you see anything that might warrant it. Ground inspections can also provide good supplemental assessment information by looking for observations related to current site conditions. The one thing to be aware of is that the inherent value of the inspection really depends on the type of hazard being assessed. So for example, as mentioned, some of these hydrotechnical hazards like scour or bank erosion will rely heavily on field level inputs from inspections or surveys, but those same methods may produce limited results for assessing the activity of a deep-seated clay landslide, which may have limited surface expression. So it's important to have that understanding when you're designing your program. And for this reason, a certain level of judgment and experience is required to facilitate that. We do typically recommend at least one ground inspection be conducted to assess site conditions for any site where an unacceptable threat is identified. However, the value of subsequent inspections really needs to be determined as part of this hazard assessment. So one of our main pieces of data for assessing pipeline conditions is this ILI IMU data, and so ideally for this, we would typically request the raw IMU data be provided to a trained practitioner who can interpret the plotted bending strain signatures to assess whether they are likely either ground movement or construction related. And we prefer to see this raw data in lieu of vendor-produced plots because we're often looking at subtle variations in bending strain signatures, which correspond to anticipated geohazard activity, and some of the automatic vendor algorithms may miss these. With only a single run of IMU, there is still a fairly high degree of uncertainty with this assessment, but identified strain growth in run-to-run comparisons, such as the one shown on screen here, can make this interpretation much more obvious. And in general, like everything else, the more supplemental information that's available to us at the time we're doing the assessment, such as LiDAR or in situ instrumentation data, the more confidence we can have in this assessment. And finally, InSAR. So InSAR can provide indications of surface movement, but it does require some interpretation to provide confidence in the results when assessing geohazard activity. This is primarily because we can't determine the hazard morphology strictly from the InSAR. We just get an indication of surface changes, so we need that kind of background understanding of the hazard morphology to ensure that the change that we're detecting is consistent with what we would expect from the geohazard. So Kris is going to get into a bit more of the technical limitations in his portion of the presentation, but I'll just highlight some key considerations from the geohazard side. So the surface changes that we detect with InSAR are averaged over a standard pixel size, and when we're talking about pipeline applications, we typically are talking about or needing dense vegetation penetration. So we're looking at L-band, which has a standard 3 meter by 3 meter pixel. And this can introduce some averaging errors, particularly when we're looking at steep slopes or undulating topography. The other thing to consider is the satellite direction, particularly relative to slopes, as topography and ground movement direction can cause changes to be either under or over reported, depending on the satellite's orientation. And then depending on the anticipated movement velocities, the detection windows may be too short to detect very slow ground movements. So we really need to consider what our anticipated hazard activity is when we're designing a program. But the key benefit here is that InSAR does allow for concurrent monitoring of a very large area. But then again, the thing to keep in mind is just because InSAR doesn't detect movement for, say, a given landslide, doesn't necessarily mean that it's inactive. So it's always important with any sort of widespread data collection to combine that with a really robust hazard screening methodology so you understand where your potential risks are. So now that you've identified and assessed hazards, moving on to the next step is what do you do to manage those? And so hazard management can consist of a series of decisions and actions that will vary according to the hazard mechanism, economic and social considerations, and the owner or operator's risk tolerance. And these can vary quite a bit from, doing nothing, being like just accepting the threat or the risk that's been identified, all the way to monitoring, mitigation, or avoidance through, say, pipeline replacement. It should be appreciated here that monitoring covers a broad spectrum of solutions, and individual monitoring plans need to be developed for each site or hazard by considering the hazard mechanism, threat level, and in the case of ground deformations, the remaining strain capacity in the pipeline. So on screen, we just have a few examples of some common monitoring techniques. This is not an exhaustive list. We don't have time to get into each of these in a lot of detail. Just know that there's pros and cons of each, and it's always good to engage an experienced geohazard practitioner when designing your monitoring program so that you ensure that you're, detecting the things that you need to detect and actually managing your risk. So when it comes to trying to reduce risk or threat from a hazard, one of the main ways we do that is through hazard avoidance on pipeline jobs. And this can take a few different forms. Some of the most common would be rerouting around a hazard, horizontal directional drilling underneath it, in the case of landslides, as shown on the graph on the left here, or installing the pipe on surface and making sure that it's somehow disconnected from ground movement, as shown on the examples on the right. Now, the key consideration for all of these is they're expensive, but they do also, substantially reduce risk from the hazard. But again, you need to be aware of the other hazards in the area. For example, you don't want to be installing a surface pipeline if you also have rockfall and debris flow hazards in the area. And, you need to make sure that if you're doing an HDD under a slope, that you make sure that you're actually getting below the maximum potential depth for the landslide. Now, in these very slow-moving, deep-seated landslides in the Western Canadian Sedimentary Basin, one of the other options we have available to us is a stress relief. And so the idea here is that if we're talking about landslides moving on the order of millimeters a year, that strain will kind of gradually accumulate in the pipeline over time. And as we get close to the serviceability limits, we may need to daylight the pipeline. And the idea here is that when we're daylighting the pipeline, we're removing that stress load and hopefully reducing some of the strain in the line to extend its capacity and lifespan. And then finally, on the more extreme side, we've got some potential slope stabilization measures. Now, these can often be cost prohibitive for a lot of pipeline jobs. But if the movement's shallow or localized to specific areas, there may be options available to us. So always worth exploring kind of a cost-benefit assessment when looking into mitigations. So that's all I had. So I'll pass things off to Kris to talk through the InSAR in a bit more detail here.
Thanks, Damian. So now we're going to get into InSAR for geohazard assessment and how to incorporate InSAR data into your geohazard management program. InSAR is a remote ground movement. It is important for the pipeline sector as it can cover large areas and doesn't require any ground-based instrumentation to get results. We can monitor thousands of kilometers in pipeline in near real time and detect movement down to the millimeter or centimeter, contingent on the vegetation level. It's important to differentiate radar images from optical images. As you can see, optical images are what we would be taken with a camera and have various purposes for monitoring linear infrastructure. What makes SAR, satellite aperture radar images, unique is the definition that can be seen on the ground below and the ability to create interferograms, which can be used for a process called InSAR. The advantages with radar images is that unlike optical images, we can actually, it works at night and we can penetrate through the cloud cover. You'll see on this animation here from the European Space Agency showing the Sentinel satellites that are currently in orbit. So the optical is a passive sensor, while the SAR is an active sensor. And here's a demonstration showing that the Sentinel satellite is orbiting the Earth and repeating passes every 12 days over certain areas on a certain frequency. SAR images captured by the satellite includes a record of the phase return for each pixel of the image. When subsequent images are acquired from the same locations, changes in the phase are used to determine the amount of displacement on the ground. In general, the satellites return on the order of a week. In most cases, for the projects we're doing in the pipeline sector, it returns every 14 days. But it's also contingent on the satellite chosen and whether it's in a constellation. New satellite constellations are being launched that will enable daily or even hourly updates in the near future. So now let's get into how to use the InSAR data in our pipeline geohazard management program. So the applications for using InSAR include finding unknown hazards. So our large area of analysis allows us to identify small areas of ground movement that are moving slowly or even more accelerations. They can also be used for managing known hazards. So typically a lot of operators have their pipelines geohazards mapped, and we can use the InSAR data over these large areas to track either historic or current areas of ground movement. So this can be used in conjunction with LiDAR, as Damian mentioned, patrols, instrumentation. So one of the key advantages is that with InSAR, we can cover lots of linear infrastructure for a limited budget. As we know, particularly in North America and other countries, these pipeline networks expand over vast areas of remote vegetated land. And of course, pipelines are built through varied topography, and they go through mountains, hills, all kinds of different corridors. So with the currently available satellite data, it is important to distinguish what works best in which area when designing an InSAR ongoing monitoring program for your pipeline. For remote vegetated areas where most of the landslide activity occurs, 3VG has access to L-band data that can be commercially tasked to acquire images at 3-meter resolution. Our various projects with large pipeline operators, the Pipeline Research Council, and PHMSA have successfully demonstrated that we can acquire data anywhere, including the boreal forests of Canada, particularly in British Columbia and Alberta, the Appalachian Mountains of the US, and the jungles of South America. The image above uses a simplified example showing how the longer wavelength can penetrate the vegetative cover. It is important to note that X-band InSAR data works great in urban locations and arid locations, and then that the C-band Sentinel data works in semi-vegetated areas and does provide valuable data for pipeline operators, particularly because Sentinel images are free and they typically have a large archive dating back to as early as 2015. So now we're going to get into some of the case studies and work we've done. So this is an area here in Alberta where field verification confirmed some landslides we found using InSAR. The image on the left highlights 2 areas in heavy vegetation with their contours in white where we detected ground movement with one of the sites near a transmission pipeline. The optical photo shows the ground movement and the level of vegetation in the area where we successfully found this landslide. I want to get into the products that 3VG has developed with the help of North America's largest pipeline operators. Our displacement rate heat map shows areas of stability in green, with the rate map of ground movement shown in red, which is away from the satellite, and blue, which is towards the satellite. Blue results typically would indicate that the ground is moving down a slope, but still towards the satellite, or it could be heave from other activities or seasonal effects, shown in cyan. The operator provides 3VG with a particular buffer on each side of the right-of-way that's typically around 500 meters, but it's dependent on the topography of the region and the level of landslide activity. And of course, that's the size of the landslides. 3VG developed customized algorithms called signal-to-noise ratio contours. These contours automatically highlight areas of statistical significance near or along the pipeline corridor with levels of confidence of ground movement. SNR 4.0 is our highest level of confidence at 99.5%. The metadata also includes the distance to the pipeline, the square area of the movement detected. So another case study here, some work we've done again here in Alberta. So this is a demonstration of what we call our rapid report, which includes the displacement rate map and the signal to noise contours. The rapid reports can be generated with as little as 6 images. For context, if we're using a satellite that acquires images every 14 days, we could generally initiate these reports within 3 months of a project kickoff. For this particular case, the operator kicked off the program in 2018. As you can see, on the left of our rapid report detected no distinguishable ground movement in 2018 or 2019, but however, in 2020, we did find 2 areas of nodal displacement of approximately 3 to 4 centimeters of movement per month, right along the pipeline corridors. As you can see in the diagram, there are multiple pipelines in this area. These landslides were confirmed by the pipeline operator and since have been mitigated. Once 3VG has acquired a minimum of 10 to 13 images, we can generate what we call a comprehensive analysis. It contains the signal to noise contours and the heat map, but also adds time series of displacement for each pixel point. This is important as we're now able to determine the rate of movement over time from the initial image to the latest and can group a cluster of pixel points and take the averages. 3VG's latest innovation, the displacement data stream, provides seamless updates to the time series upon each subsequent image acquisition. This allows for a quick near real-time update to the data set and improves the ability to detect slope creep as the time series matures, which is very important to the geohazard management, as slope creep is below LiDAR's threshold of detection and typically not visible optically. I'm going to get into another case study here. So this is from our paper published at Geo Niagara in 2021. Multiple landslides along the North Saskatchewan River were detected with 3-meter resolution ALOS-2 ongoing InSAR monitoring. Freely available Sentinel data had insufficient data coverage to provide meaningful results. Our results identified an unknown landslide where the operator used our data and eventually decommissioned the pipeline. So here is an example of some work we are doing near Fort McMurray. So we have a long 5-year multi-year data set here, and we have shown that with sufficient images over a long time frame, over multi-year analysis, we can get approximately 2 centimeter per year precision, if even better, in these areas where we've got these long image acquisitions over the time. So this provides much better, much more frequent updates than what would be possible with LiDAR. And again, it just shows that we can get much better change detection as far as the precision levels than what could be done with LiDAR over a similar area of interest. Here's another case study of some work we have done in the Arctic, so the Northwest Territories. So InSAR can be used to map permafrost. A case study above illustrates how InSAR can provide data to differentiate landslide signals from seasonal signals like subsidence and heave from permafrost melt and freeze. The image on the left-hand side clearly shows an acceleration of ground movement into a water body, whereas the seasonal signal on the right repeats as we acquire data over multi-year timeframes. Another case study of here is some work we have done in the Pennsylvania Appalachia region. So we used InSAR to track longwall mining subsidence along a corridor with multiple operators' pipelines. The data was then used to compare with strain and LiDAR results and showed good parity with the results from the other means of monitoring. So here's some of the questions we get when we are developing an InSAR program with pipeline operators. So a typical question is how large of an area can you detect using InSAR? So this is where the resolution plays a key factor. Our typical projects incorporate 3-meter resolution data, but we need a certain number of pixels moving in unison to generate reliable data. For ALOS-2, the minimum detectable area is approximately 576 square meters, although we have detected smaller areas in the past. For comparison, using Sentinel's freely available data, the minimum detectable area is in approximately 160 meters by 40 meters. So it's important to note there are limitations with InSAR. Damian went through some of them. InSAR, like most pipeline monitoring technologies, does have limitations. I'll highlight a few to consider when implementing an ongoing InSAR monitoring program. InSAR relies on the comparison of the same points or areas on the ground between images. This means that the same land area must be present and be structurally similar each time the sensor images the ground. If modifications are made from construction, digging, dumping, tilling of the soil, measurements for that period of activity are destroyed. However, once activity has stopped, we are again capable of resuming to acquire measurements. Another key factor is snow, particularly in Canada and other regions. Snow obscures the surface and prevents measurements. However, measurements that span the snow coverage can often be made. Another limitation is shadow. So shadow can pose an issue, particularly when monitoring hilly or mountainous terrain. The satellite can't look over the top of the mountain, therefore there's no data on the other side. This can be overcome by collecting ascending and descending data. Another limitation that we've known, particularly in areas where there is substantial swamps or bogs or vegetation and water, soil and moisture signals from water with vegetation are not currently differentiable from ground movement signals. We are working on machine learning to differentiate these signals. As part of our feasibility study, 3VG can generate maps showing likely data quality. So if you are looking to start and incorporate InSAR into your geohazard management program, this slide here highlights the time frame to acquire the data. So 3VG can produce a report with as little as 6 images and can generate update reports every image or second image thereafter until we have a minimum of 10 to 13 images. Once we have those 10 to 13 images, we can regularly update the comprehensive analysis thereafter. Initial reports can be issued in as little as 3 months and can be updated monthly. As the time series lengthens, so does the quality and the detection level, the level of detection. So now we are going to get into a demonstration of 3VG's proprietary web viewing platform titled Motionary. This data set is in British Columbia, Canada, in an area with hilly terrain, very limited access and heavy vegetation. And there is snow cover in this area from November to March. We use JAXUS ALOS2 for this analysis. And as we show, the footprint covers approximately 50 by 70 kilometers for a total of 3,500 square kilometers. Motionary has the ability to change measurement units between metric and imperial, so that's important for people in the US. As we scroll into our data, the many SNR contours become visible. The color scale bar on the left-hand side can be adjusted to show maximum displacement. Right now, we've changed it to 36 centimeters per year, but we can be adjusted according to what's needed for the program. And we're going to switch back to imperial now for the demonstration. But as you can see in the area we're showing, there are many contours of large areas of displacement in the data set. We're now focusing in on a specific area of ground movement along a slope near a water body. As we zoom in on each individual pixel points, areas of displacement are shown in red, while other areas of stability are shown in green. We can use the polygon tool to draw an area to show the time series of those points. It shows the average plus the time series for all selected points. The white lines in the time series with dates underneath represent each image acquisition. They also contain the rate of displacement over the length of the acquisitions. Motionary also has this option to switch from time series to velocity, which shows the average velocity on the specific date selected and the total over time. Switching over to the stats tool shows various statistics over the selected points. We will cycle through each of them now. So there is also a download function. We're just going to show you the time series as a larger screen here. And then, yes, there is also a download function allowing users to save the selected data over the AOI in their preferred format. So that includes a CSV file, a shapefile, or KML to import into other software. We will now scroll out to a larger AOI. This tool here allows us to show the 3D rendering of the selected data points. The 3D rendering can be viewed and rotated 360 degrees. Again, each data point is clickable in the 3D view to pull up the time series. As you can see, this is a shorter time series for this area of analysis. So several areas denoted as moving away from the satellite, particularly down a slope. Switching back to the heat map now, we can insert thresholds here to filter out results that are not of interest for the geotechnical engineer analyzing the data. So these are all fully adjustable. But as you'll notice, the data does become noisier as we shift the slider to display smaller amounts of displacement, which is mostly due to the short length of the time series. As more images are acquired moving forward, the quality of the data enhances to similar to some of the data we have in other regions of North and South America. So that is the demonstration of motionary. I will now to the next slide and pass it back to Damian for some demonstration on how to interpret the InSAR data.
Thanks, Kris. Yeah, so this is some sample data we were provided near Edmonton and asked to interpret. So I'm just going to quickly run through. Basically, we've just proposed like a 5-category confidence interval for our interpretation, with the category 1 being our highest level of confidence that the change detected in InSAR is actually corresponding to geohazard activity, and category 5 being the lowest, where we don't think anything's really going on. So first example is a category 1 site. This is kind of our, optimal interpretation, where we have LiDAR showing clear landslide morphology that is kind of perfectly aligning with the change detected by the InSAR data. So this is a fairly clear-cut case. The movement shown in the InSAR is aligning with what we would expect from the landslide mechanism. Category 2, we've got potential ground movement with the presence of an active driver and historical landslide activity in the area, but either the change detection in the InSAR isn't super clear, or it's not perfectly aligning with what we're seeing in the LiDAR. So this could be an indication where the landslides on the bank of the river have expanded here, because they are in an area with historic landslide morphology. There is active erosion at the toe, all these potential drivers for ground movement, but we're not 100% confident that it's occurring. Now, category 3 is there's maybe some potential movement, possibly an active driver, but we don't see any historical indications of landslide activity. So in this example, you can see the change detected is up on a fluvial terrace. So while there is some bank erosion and those kind of active processes going on right beside the river, up where the change is detected, it looks like it should be fairly stable, but we can't say with 100% confidence that nothing's going on. So it's kind of in our mid-range. And then category 4, we're getting down to this is either like we'll have less data available to make the interpretation, or we don't really think anything's going on. So like in this case, we're looking at what should be a fairly stable highway embankment that's showing some kind of muddled superficial changes, but there's no real active driver, no historic landslide activity. We don't really think anything's likely happening here. Then category 5 is where we're fairly definitively certain that nothing's going on. So in this case, we've highlighted some superficial changes, but as you can see in the aerial imagery, those are likely just due to changes in the active stockpile there. And with that, I will pass it over to Kyle to wrap things up.
Thank you, Damian. So we've had a couple good questions come in. Looks like we're definitely going to have time to talk about some of those in person at the end. But before we do that, I'm going to talk just a bit on in-situ instrumentation and a few of the things that the Terra Insights platform offers. It's important here to work with a consultant who really knows what they're doing, such as Thurber, to thoroughly design your monitoring program here. I'm just going to talk about a few things that you could do that we offer. And we're going to start with kind of some sensor basics, which will be a little too basic for many of you, but it's important to understand the basics when we talk about shape arrays and how those work, things like that. So a few of the things that we're going to touch on would be MEMS chips, also known as accelerometers on the right, as well as just types of strain gauges and sensors that can read stress. So if you hear the word strain gauge, most of the time, what people would be talking about would be an electrical resistance strain gauge. So that's going to be a wire printed on the chip. If I stretch it out, it's going to be more electrical resistance. So it's going to be a measurable change in resistance, which is correlated to strain. In geotechnical instrumentation, a lot of the time we're doing vibrating wire strain gauges, which is actually a wire tension between 2 points, kind of like a guitar string. If I tighten it, it's going to vibrate at a higher frequency. If I loosen it, it's going to vibrate at a lower frequency. So calibrated in the lab, I can pull all sorts of data from that. I can hook it up to a diaphragm for a piezometer. I can weld it onto a pipe as a strain gauge, that type of thing. We're using those most of the time because they're very reliable, stable readings. You can get away with very long cable lengths. And with a thermistor attached, you can very carefully calibrate for changes in temperature. A bit more expensive than resistance strain gauges, but important to understand that a lot of times, at least for pipelines and that type of thing, vibrating wire strain gauges are used fairly often. The last thing, MEMS chip, you can think of it like a mass suspended between capacitive plates. And if I rotate those plates, I'm going to get a measurable change in capacitance. So that's going to give me tilt relative to gravity. Those principles, there's a lot that I can do. You see on the top left, this would be a spot weldable vibrating wire strain gauge. On the left middle, that would be a MEMS tilt meter. Bottom left would be a vibrating wire piezometer. Why would you install piezometers? Well, changes in pore water pressure, an increase in pore water pressure might correlate to reduced shear strength, which could decrease your safety factors for slope failure. That data combined with changes in stress in the pipe could be fairly telling. On the right side, you see an in-place inclinometer made by RST, and the far right would be a shape array manufactured by Measurand. So everything on this page is going to be vibrating wire or MEMS chips, and there's a lot that you can do with that. So strain gauges, usually you'd install those in maybe a 9 o'clock, 12 o'clock, 3 o'clock pattern. And if you plot the change in microstrain over time, and you start to see that maybe the 9 o'clock is increasing in tension and the 3 o'clock is increasing in compression, then that might actually be something that you should investigate manually. Or maybe you've done this after a strain relief project, as Damian was discussing. You could also attach tilt meters directly to the pipe itself. And if you know the distance between your tilt meters, you can get a pretty cool profile of the pipe in the same way that you would with an inclinometer, actually. Inclinometers, you might install those within the potential failure surface. It's important to anchor that casing well into a stable layer, such as a glacial till or bedrock, so that the casing isn't just floating around. You can see a manual inclinometer probe. Most of you are probably pretty familiar with that, and you understand the concept of taking those measurements. I'm American, so every 2 feet for me, but fixed length with a known tilt, and you can get a profile of the entire borehole. Now, a lot of times what we're seeing is boreholes are in remote locations. We don't want to send engineers out there to monitor them at a frequency that's available. So the shape array and in-place inclinometers have filled this void of real-time monitoring. Shape array, same MEMS chip you would have on a tilt sensor or a manual inclinometer probe or an IPI, but it comes on a real pre-calibrated. It will give you its shape relative to gravity. So no calibration needed when you show up on site, and you just unreel it into the borehole, compress it so that those segments are flush with the borehole, and then you can get very accurate readings very frequently of slope deformation, so you might detect failure before it occurs. Lots of cool ways to view the data here. You can do cumulative displacement, you can look at cross sections, but one of the things that's most valuable with the shape array is its ability to tolerate large deformations. So on the right there, you see a casing that maybe has a bend in it with a manual inclinometer probe, and that probe just can't traverse that bend. Well, the shape array is a lot narrower and sometimes is used to retrofit inclinometer casing that may be failing. If that's the case, then really you should start paying more attention to it anyway. So maybe readings every hour are going to be valuable to you. You can also see a slope failure that did occur here. This is not a pipeline, but it's in my home state of Minnesota. And this is a case where the shape array tolerated, the x-axis there is inches, so it tolerated 100 inches of lateral movement and continued to read, which you're going to have a hard time doing that with manual inclinometers. So considering all those different sensor types, what do you do with the data? Well, in the old days, we would hook it up to a Campbell Scientific logger or a multiplexer, as you see on the left. Sometimes that would be connected to a cell modem or a satellite modem if you're in a more remote area. These days, most loggers are moving towards a wireless system. You can see our R-Star Affinity system on the right with our gateway and our nodes. Those can be set up in a LoRa network or a smart mesh. And one of the things I like about those nodes, we talked about vibrating wire, strain gauge, tilt sensors would be an RS-485 bus. You can set up the node loggers to accommodate really any combination of those sensor types and do away with some of this complicated wiring. So this wasn't the focus of the presentation, but I did want to just kind of touch on some of the things that Terra Insights can offer in addition to just InSAR. So with that, we're going to hand it over to Kris to talk a little bit about, say you're thinking about InSAR, what do you actually need to turn it into a feasibility study or a project?
Great, thanks, Kyle. So getting started with InSAR, what are the next steps? So typically when we're designing an InSAR program with a pipeline operator, we would request the center lines and the specific areas of interest where there is ground movement activity that is of concern. Approximation is fine as we do have very large footprints to cover the infrastructure. And it's also contingent on the type of displacement that's of concern as well. InSAR isn't great at capturing fast-moving mudslides or fast-moving landslides, but is better at detecting the slow, more creeping type of landslides. And of course, having either off-the-shelf LiDAR and available data for geohazard screening to support the assessment is critical as well. If we can use the high-resolution LiDAR DEM in our data, that would definitely helps the InSAR results moving forward. And from there on, we can craft a package directly with the operator on a certain reporting frequency and let them know what the image acquisition schedule looks like and decide what type of data would be best to acquire based on the precision and the levels of vegetation. Now can we move forward to the questions? Or actually, sorry, Damian.
Yeah, just please chime in to say that, we can do the interpretation with, publicly available data, just as I think mentioned in my presentation there. There's a lot of value added if we have this, at least, one data set for LiDAR to help with that morphology interpretation. Yeah. Okay, do we want to jump into questions?
I think so. Let's see here. So I promised in the chat that I would respond to Ali from Critical Crossings first. And I think this was back, let's see if I can, this was back when Kris was talking. The question says, maybe misunderstanding, but the minimum distinguishing length being 8 meters, how do you recognize a 1 to 2 millimeter displacement for slope monitoring? And I think that might have been related to the ground resolution. I don't know if you want to talk a little bit about how you're actually just getting that 1 to 2 millimeter precision on the displacement.
The 1 to 2 millimeter precision would be the superficial change on the ground. So there's 3 different wavelengths available: X band, C band, and L band. The majority of the case studies we showed were, in fact, the L band, the longer wavelength that penetrates through the vegetative cover. However, in areas where arid areas or urban areas or mining sites, X band has the capability of getting that 1 to 2 millimeter precision, so the actual amount of ground movement. So precision is different from resolution. So resolution is the size of the pixel point, whereas precision is the amount of displacement we can detect. Hopefully that answers the question.
Gotcha. So another one, this one, we've got a team kind of answering a few questions via the chat, but the question was from Prabeen of the University of Alberta. And the question was, which image sources do you prefer to use for the optical and radar images? Is getting a good / high resolution historical image a problem? I'll read the response here, and maybe Kris, you can expand on that. But our response was, SAR images are collected by 3VG in SLC format and are processed before being delivered to Motionary. Ordering historical imagery at high resolution is nearly always possible for any project. Usually projects include archive imagery to get the project going as fast as possible for a client. So Kris, do you have any additional thoughts on optical versus radar images and whether that historical image is always available, or did that kind of answer it?
That mostly answers it. 3VG doesn't really specialize in collection of optical data. There's other vendors for that platform. There is there's 20 meter resolution data available all over most of the Earth through Sentinel. That's freely available. But typically, as we get into the commercial satellites like TSX and CSK, they will have higher resolution archives in certain areas. So if you do have a particular area of interest, we can go and look at the archive historically and let you know what's available at a higher resolution.
Gotcha. So this next one, this is from Shiv Prasad of the CSIR National Geophysical Research Institute. And the question is about three-dimensional displacement data. And I think what he's getting at here, if we look back to maybe some case studies where we've evaluated buildings, for example, a lot of the displacement data for landslides would be in the Z direction. Would dual look help you there? Am I on the right track, Kris? Or how do we go from just vertical displacements to actually getting a bit more?
InSAR is a two-dimensional product when we have both look directions. So that would be ascending and descending passes. We can combine those to get both vertical displacement and then also east-west displacement only for horizontal results.
Gotcha. We have a question from Marvin about cost comparisons for SAAs, tilt meters, and InSAR. And I'm hesitant to really answer this one because I think that they should be used together. I don't think it's a either or scenario. But 3VG is happy to provide one-off cost estimates for InSAR. I'm happy to do the same for SAAs and tilt meters, but a single tilt meter might be around $500. A shape array is going to vary based on the segment lengths, but is going to be, since the segments are closer together, at the same spacing versus an IPI, the shape array will be more expensive than the IPI at like a 5-foot bay rod. There's a lot of variables there. So my response would be, it's our job to answer that one on a project basis.
Yeah, I think that ties back to my point of needing like a fit for purpose monitoring program too, right? Because like each of these techniques, like the InSAR is going to be better for widespread monitoring of surface movements, but the SAA is really starting to drill down to that detailed site level interpretation, seeing what a landslide's doing at depth. So it really takes an understanding of the hazards that you're trying to manage to kind of, figure out what the best option is.
Yeah, completely agree. This is kind of a fun one, and the answer might just be no. But the question is from Juan, and it's about seismic events. And I don't know, Kris or Damian, have you seen InSAR used maybe in a historical sense to see the impacts of seismic events, or possibly to, I'm not sure how you'd use it for prediction, but maybe you have some insight on that.
That's more of an educational pursuit. So you see a lot of the universities in the States and other areas doing research on applications for using InSAR to monitor for earthquakes. Let me just see if we've got one of our colleagues has sent an answer here.
Yeah. We'll table that one and see if anyone on the chat has any comments. But this one's kind of interesting to me, and this might be a good question for Damian, which is just related to geophysical testing on site. So is that something that Thurber gets involved in to complement more InSAR?
Yeah, we'll quite often recommend geophysics programs for various applications. So I think, sorry, just to clarify the question for everyone was, do you use any geophysical tests alongside image analysis and on-site instrumentation? So short answer, yes. But again, they need to be fit for purpose. It really depends on the application and what sort of information we're trying to acquire.
Gotcha.
So I've got some furtherance on the seismic here. So obviously seismic refers to earth vibration like earthquakes. We can measure tectonic plate shifts, but not vibration. We can measure damage from earthquakes, but not the vibration itself. So we did a bit of work in California on earthquakes where we could show where, I guess, the most fracture possible area was on the gas pipeline.
Got it. So I think the last question that we're going to answer in person here before we wrap up, and we'll try some of these, it might be better to answer directly, so we'll reach out to you on an individual basis. But I think the last question we're going to take is related to managing uncertainty of measurements without a whole lot of historical data. And you might have touched on that earlier, Kris, in terms of just how many images you need to have some degree of certainty. But, is 14 enough? Is 20 enough? What's the tipping point there? And so we'll read the full question. How do you manage uncertainty of measurements with InSAR in case there isn't too much historical data? And that's coming from Saeed at the University of Alberta.
As we mentioned in the presentation, we need a minimum of 6 images to start to filter out some of the noise and other uncertainties with the data. But as you said, as we get to that 13 to 15 image range where we can generate the time series, that's when the noise reduces enough for us to get more certain results with our InSAR analyses.
Yeah, and then I think to the point on the detection interval, like if your detection interval is too short to really get an understanding of the landslide activity, that's when we would have to turn to other assessment techniques to supplement the InSAR as well until the detection interval had progressed long enough that we started to get an idea of the movement rates. So that's where we might start looking at, depending on the level of threat posed from the landslide, we might start looking at installing in situ instrumentation or looking at IMU data for the pipeline if it's available, those kind of things.
And it also helps when images are acquired more frequently. So the longer the gap in the image between the image acquisitions, the poorer the data will be.
Awesome. I'm satisfied with that answer. Let's wrap it up. We are 1 minute early, so we'll give you 1 minute back here. But please expect a follow-up for all attendees, and some of these specific questions we'll get back to you on an individual basis. So thanks for joining us.
Awesome.
And thanks to Damian and Kris.
Thanks, everyone. Cheers.